Fine. After J.J. Thomson, we have a man called Ernest Rutherford. So what is Rutherford's model of an atom? Okay. So he didn't suggest a illusionary model. Okay. அவர் என்ன பண்றாரு, ஒரு எக்ஸ்பெரிமெண்ட் கண்டக்ட் பண்றாரு. We call that the gold foil experiment. Rutherford's gold foil experiment. இவர் Ernest Rutherford இந்த எக்ஸ்பெரிமெண்டோட செட்டப் வந்து you will see it on the screen. There is a green color part on the screen. அது என்னன்னா, it is a scintillating screen. Scintillating screen அப்படினு சொன்னோம்னா, that screen is coated with a fluorescent substance. Fluorescent substance அப்படினு சொன்னோம்னா, it will create a glow when a charged particle falls over it. அந்த screen மேல ஒரு charged particle விழுந்தது அப்படினு சொன்னோம்னா, it will give you a glow. Okay, அது வந்து ஒரு scintillation create பண்ணும். அந்த scintillation வைத்து அங்க சார்ஜஸ் மேல உழுந்துதா உழுலியான்றத நம்மளால சொல்ல முடியும். Okay, based on the scintillations that are produced. Okay, now I will explain what is Rutherford's experiment. Okay, இப்ப இங்க ஒரு பாக்ஸ் மாதிரி இருக்கு இல்லீங்களா, இந்த பாக்ஸ்ல என்ன பண்றாரு Rutherford வந்து he places a alpha particle. Understand? ஒரு radioactive substance அத வைக்கிறாரு. அந்த radioactive substanceல spontaneous emission of radiations இருக்கும். When radiations are emitted spontaneously, okay, we get alpha, beta and gamma rays, of which Rutherford selects only the alpha particle. Alpha particles are normally positively charged. Okay, they அது என்ன கம்பேர் பண்றாங்க alpha particles helium nucleus க்கு கம்பேர் பண்றாங்க. Understand? Alpha particle is nothing but a nucleus of a helium atom அப்படினு சொல்றாரு Rutherford. So here the alpha particles என்ன பண்றாங்க, they are accelerated and made to move fast, and அத வந்து என்ன பண்றோம், we are making it to fall over or pass through a gold foil. இங்க ஸ்லைட் green கலர்ல ஒரு சின்னதா ஒரு ஷீட் ஆஃப் கோல்ட் இருக்கு பாருங்க, அதுதான் வந்து கோல்ட் ஃபாயில் சொல்றோம். ஃபாயில்னா நம்ம வீட்ல வந்து அலுமினியம் ஃபாயில்னா நம்ம யூஸ் பண்ணிருப்போம். ஓகே, they are thinner ones, very thin by nature. இந்த அலுமினியம் ஃபாயில் வந்து ரொம்ப மெலிசா இருக்கிற காரணத்தினால இந்த ஆல்பா பார்ட்டிகல் அது வழியா எளிதா உள்ள பூந்து அந்த பக்கம் வெளியில வர முடியும் ஆல்பா பார்ட்டிகல்ஸ்னால. இப்ப இந்த எக்ஸ்பெரிமெண்ட் செட்டப் இதுதான். ஓகே, அந்த கோல்ட் ஃபாயிலை சுத்தி ஒரு சர்க்குலர் செமி சர்க்குலர் ரீஜன்ல scintillating ஸ்கிரீன் வச்சிருக்காரு, fluorescent ஸ்கிரீன் வச்சிருக்காரு. இந்த fluorescent ஸ்கிரீனுக்கு நடுவுல கோல்ட் ஃபாயிலை வச்சிருக்கோம். இந்த கோல்ட் ஃபாயிலை நோக்கி ஆல்பா பார்ட்டிகல்ஸ் அவர் பாஸ் பண்றாரு. So what is the observation of Rutherford? Okay, that's fine. So you find the particles moving in a straight line through the gold foil. Most of the alpha particles, you see here on the other side of the gold foil, most of the particles are traveling in a straight line and falling over the scintillation screen. அது எப்படி கண்டுபிடிக்க முடியும்? ஆல்பா பார்ட்டிகல்ஸ் தான் நம்மள கண்ணால பார்க்க முடியாது, ஆனா அந்த ஸ்கிரீன் மேல விழும்போது ஒரு ஸ்பார்க்கை கிரியேட் பண்ணும். It will create a spark. Understand? We call it scintillations. So when it falls over, what will happen? And the spark visible ஆகும்போது அப்போ ஒரு charged particle அது மேல படுது அப்படின்றத நம்ம தெரிஞ்சுக்க முடியும். So there are other particles also falling over the sides. இங்க பாருங்க, ரெண்டு பார்ட்டிகல் இந்த பக்கம் உழுறது பாக்குறோம். So that is the observation of Rutherford. There is another particle that is not passing through. It is reflected from the gold foil and falls behind the screen. முன்னாடியே இங்க விழுந்தது ரிஃப்ளெக்ட் ஆகி. இந்த மூணு observation, the first one என்ன, most of them were able to pass through the gold foil and fall over the scintillating screen. A very few, okay, got deflected and are falling sideways. ரொம்ப fewer particles என்ன உள்ளே பாஸ் பண்ணல, they are getting reflected and they are falling behind the screen. இதுதான் Rutherfordோட observation. Okay, based on these observations, Rutherford suggested the model of an atom. இந்த மேல ஒரு டயகிராம் இருக்கு பாருங்க, இந்த ரெட் கலர் இருக்குது இல்லீங்களா, this region is the nucleus of an atom. Okay, the red color region. And what is shown in dotted, அதுதான் வந்து electrons இருக்கக்கூடிய இடங்கள் அப்படினு assume பண்றோம். பின்னாடி ரூதர்ஃபோர்ட் அப்படிதான் அஸ்யூம் பண்ணிக்கிறாரு. ஒரு பாசிட்டிவ் நியூக்ளியஸையும் அதை சுத்தி வந்து எலக்ட்ரான்ஸையும் அஸ்யூம் பண்ணிக்கிறாரு. இப்ப இந்த அப்சர்வேஷன்ஸ் வச்சு அவர் எப்படி எக்ஸ்பிளைன் பண்றாரு ஆட்டம் அப்படின்னு சொன்னோம்னா, most of them are able to pass through in a straight line அப்படின்னு சொன்னோம்னா, இங்க நல்லா கவனிங்க. இந்த இதுதான் ஆட்டம் அப்படின்னா, இந்த கோல்ட் ஃபாயில்ல many number of atoms of gold இருக்குது. அதுல ஒரே ஒரு ஆட்டம் மட்டும் தான் இங்க காட்டிருக்காங்க. அப்ப இது எப்படி அரேஞ்ச் ஆயிருக்கும்? இதே மாதிரி இன்னொரு நியூக்ளியஸ், அதை சுத்தி எலக்ட்ரான்ஸ், இது மாதிரி ஒரு ஸ்ட்ரெயிட் லைன்ல ரவுண்ட் ரவுண்டா இருக்கும் இல்லையா ஆட்டம்ஸ். இப்ப அதுல ஒரு ஆட்டம் எடுத்து தான் நம்ம எக்ஸ்பிளைன் பண்றோம். மோஸ்ட் ஆஃப் தம் ஆர் ஏபிள் டு பாஸ் த்ரூ அப்படின்னு பார்த்தோம்னா, இங்க ஒரு நியூக்ளியஸ் இருக்குது, இங்க ஒரு நியூக்ளியஸ் அஸ்யூம் பண்ணிக்கோங்க. இந்த ரெண்டு நியூக்ளியஸ்க்கு நடுவுல நிறைய ஸ்பேஸ் இருக்குது. அப்ப அந்த ஸ்பேஸ்ல வந்து ஆல்பா பார்ட்டிகல்ஸால நேரா டிராவல் பண்ண முடியுது அப்படின்றது ரூதர்ஃபோர்டோட எக்ஸ்பிளனேஷன். The space between the two nucleus இருக்குது பாருங்க. இந்த space between the two nucleus, there are more number of alpha particles that are passing in a straight line. That is what is Rutherford's explanation. So அந்த ஸ்பேஸ்ல வந்து ஒரு ஆல்பா பார்ட்டிகல் என்ன சார்ஜ் முன்னாடியே சொன்னேன் நானு, it is positively charged. So ஒரு positively charged particle, if it is able to pass through that empty space in a straight line, what does it mean? இந்த இடத்துல என்ன இருக்குதுன்னு அர்த்தம், இந்த இடத்துல நெகட்டிவ் சார்ஜஸ் இருந்தால் மட்டுமே அந்த பாசிட்டிவ் சார்ஜஸ் without any deflection நேரா அனுப்ப முடியும். Are you able to get that? Okay, there is a lot of empty space here, and only if those empty space is filled with electrons which are negatively charged, the positively charged alpha particles will be able to pass through them without getting deflected, because the negative electrons will try to attract the positively charged alpha particles. So the space between nucleus of atoms is larger அப்படினு சொல்றது. எப்படி சொல்றாரு? இந்த ஒரு காரணத்தினால சொல்றாரு. Okay, so the second one is, you find one particle which is closer by. இப்ப இந்த ray of alpha particle பாருங்க, இது நேரா போகுது, அந்த நியூக்ளியஸ் கிட்ட போகும்போது என்ன ஆயிடுது, ஸ்லைட்டா டிஃப்ளெக்ட் ஆகி வெளில போயிடுது. அது எங்க இந்த டயகிராம்ல பாருங்க, if an alpha particle has gone very closer to the nucleus, what would have happened? It would have got deflected and it would have turned. அப்ப அது வந்து very few தான் அப்படினா என்ன அர்த்தம், the nucleus of an atom is very very small. According to Rutherford, he says that the nucleus of atom is very very small. The reason is because, okay, only a few particles which were very closer to the nucleus got deflected and went elsewhere. The third possibility that is being explained is, an alpha particle which directly hits the nucleus will get reflected and turned back. That is the third case. அப்ப ரொம்ப very few தான் அங்க பாத்தீங்கன்னா, most of them are here, very few, still a very few in number, only one is here as in the diagram. அப்ப நியூக்ளியஸ் ரொம்ப சின்னதா இருந்தால் மட்டுமே டைரக்டா போய் நியூக்ளியஸ் மேல இடிக்கிற ஆல்பா பார்ட்டிகல்ஸ் very fewer நம்பரா இருக்க முடியும். Imagine the nucleus is very large, what will happen? More number of alpha particles will hit over them and get reflected. So based on the observations of the experiment, gold foil experiment la Rutherford oda observations are based பண்ணி தான் Rutherford suggested the atom model. And what is that atom model called? It is called the planetary model of an atom. So this model of an atom, as suggested by Rutherford, is called the planetary model of the atom. As sun is the center of the solar system, the nucleus is the center of the atom. Okay, and surrounding the nucleus, the electrons go around in orbits, okay, which we call them as energy levels. Okay, so அப்ப என்ன சொல்றாரு Rutherford? Nucleus இருக்குது, nucleus குள்ள positive charged protons are there, அதனால தான் alpha particle பாசிட்டிவா இருக்கும்போது நேரா போய் இடிக்குது. அப்ப position of protons எங்க இருக்குதுன்னு சொல்லி இருக்காரு. He is saying that it is inside the nucleus. And where are the electrons? The electrons are moving around the nucleus in circular orbits. and this is what is Rutherfords model of an atom. Okay. After Rutherford, we come to the Bohr's atom model. The Bohr's atom model வந்து இதுல பெரிய மாடிஃபிகேஷன்ஸ்லாம் இல்ல. ரூதர்ஃபோர்டோட atom modelல ஒரே ஒரு drawback மட்டும் ரூதர்ஃபோர்டால எக்ஸ்பிளைன் பண்ண முடியல. So the electrons that are moving in a circular orbits, okay, when they are moving in circular orbits, the tendency of any object that moves in a circular path is to lose energy. That is the concept in physics. எந்த ஒரு பொருள் ஒரு ஆர்பிட்ல நகர்ந்து கொண்டிருந்தாலும் அதை நகர்வதன் முன்னிட்டு, okay, because of the virtue of his motion சொல்றோம், because of it moving, it will lose energy. அது மாதிரி எனர்ஜி லாஸ் ஆச்சுன்னா எலக்ட்ரான்ஸ் என்ன பண்ணும், ஆர்பிட்ல சுத்திட்டே இருக்கும், சுத்த சுத்த எனர்ஜி லூஸ் ஆகும் போது பாசிட்டிவ் நியூக்ளியஸ் என்ன பண்ணும், அந்த எலக்ட்ரானை நியூக்ளியஸை நோக்கி இழுத்துக்கிட்டே வரும். ஏன்னா பாசிட்டிவ் எனர்ஜி அதிகமா இருக்கும், நெகட்டிவ் எனர்ஜி கம்மியா இருக்கும். அப்ப when it comes near the nucleus will attract the electrons and the electrons will get merged with the nucleus. ஆனால் அது நடக்குதா ஒரு ஆட்டத்துல அப்படின்னா கிடையாது. அதனால வந்து ரூதர்ஃபோர்டோட எக்ஸ்பிளனேஷன்ஸ் கொஞ்சம் தவறுதலாக இருந்தது. நெயில் போர் என்ன சொல்றாரு, நெயில் போர் வந்து இதுக்கு ஒரு எக்ஸ்பிளனேஷனை கொடுத்து ஆட்டம் மாடலை ப்ரொபோஸ் பண்றாரு. அந்த ஆட்டம் மாடலை ப்ரொபோஸ் பண்ணும்போது there are orbits around the nucleus which Neil Bohr calls them as energy levels. So in the energy levelsல ஒரு prescribed number of atoms தான் இருக்கும், sorry, electrons தான் இருக்கும்னு சொல்றாரு. வெளிய particular number of electrons will be present in the energy levels. Okay, the other electrons will be present in different energy levels. That is what is the explanation given by what do you call that, Neil Bohr. Okay, அப்ப இந்த energy levelsல electrons நகரும் பொழுது they won't lose energy. That is the explanation of Neil Bohr. So when electrons are present in the respective energy levels, electrons, even if they are moving in a circular orbit, they will not lose energy. That is the explanation that is given by Neil Bohr. Okay, so this is what is atomic structure. So according to Bohr's atom model, என்ன சொல்றோம், center of the atom is the nucleus, and inside the nucleus we have protons and neutrons, and surrounding the nucleus we have electrons. இப்ப ஒரு atom எடுத்துக்கிட்டு, for example oxygen, write down the electronic configuration of oxygen அப்படின்னு சொல்லோம்னா அதை எப்படி வரையணும் அப்படின்றத நம்ம இப்ப டிஸ்கஸ் பண்ணலாம்.
The plum pudding model of an atom was one of the most widely accepted models all over the world for understanding the structure of the atom. However, several experiments performed by scientists to study the atomic structure showed astonishingly different results. They were contradicting the plum pudding model. This led many scientists all over the globe to reconsider the structure of an atom and study it again. Around the year 1911, a British physicist, Ernst Rutherford, carried out the famous gold foil experiment. He did this to understand the structure of an atom. The experiment was carried out by Rutherford along with Hans Geiger and Ernest Marsden. The experiment he performed was a breakthrough in the field of chemistry which helped him understand the structure of an atom in a more accurate manner. This is how the setup of his experiment looked like. As we can see here, he used a source of alpha particles locked in a lead container with a very small slit. This ensured that the alpha particles only came out through a small opening and travelled in a straight line. But why did he select alpha particles in the first place? Well, the alpha particles were having high energy and were heavier as well. So if we say the atom is like a pudding of positively charged particles with electrons embedded in it, then the particles will pass straight through it. This is obvious because the heavier particles will pierce through the lighter pudding structure of the atom and pass through it. This is what Rutherford thought. For this reason, their greater mass and energy compared to the protons made him choose alpha particles for the experiment. Next, he used a very thin gold foil on which the alpha particles would bombard. Why did he choose a gold foil? Well, a really thin gold foil was estimated to contain approximately 1000 atoms. Lesser the atoms, more convenient the experiment would be. Lastly, are we able to locate this circular band with a gap here? What could this be? Well, this is the screen, a fluorescent screen that would help us detect the radiation. That means the screen will glow or emit fluorescent light whenever alpha particles will hit it. So this is how the track of alpha particles can be traced. Now we're all set to understand how the experiment worked. The alpha particles were emitted from the element present in this box. These directly hit the gold foil. Now what should happen ideally? As we know, the Thomson's model suggested that an atom is a sphere of positive charge with negative electrons embedded inside it. That means it is expected that the alpha particles will pass right through the atoms and hit the detector straight. And why so? Because the mass of alpha particles is heavier than the mass of positive charges. That means they should directly hit the atom and move ahead through it. Only a very small deviation would probably be acceptable in this case. But is this what he observed? Not really. He was astonished to get unexpected results. What results did he get? He found that most of the fast-moving alpha particles passed straight through the foil and hit the detector. However, some particles got deflected by small angles. And lastly, to his astonishment, few alpha particles also rebounded. Now, how can this be possible? These three observations made Rutherford think that the plum pudding model is not really correct. Based on the conclusions he had, he put forward the new hypothesis explaining the structure of atoms. What were his conclusions? Let us have a look at the conclusions by Rutherford, followed by the new atomic model put forth by him in the next video. Rutherford's gold foil experiment gave him interesting results. What results did he get, by the way? Let me recall them for you. He found that most of the fast-moving alpha particles passed straight through the foil and hit the detector. However, some particles got deflected by small angles. And lastly, to his astonishment, few alpha particles also rebounded. Now, how can this be possible? These three observations made Rutherford think that the plum pudding model is not really correct. Let us take a simplified example to understand the inferences first. Let us imagine that we have a ball made up of cotton. The cotton in the ball is very sparsely distributed and has an extremely tiny circle or sphere located at the center. This sphere is quite hard and dense. So hard that it can even resist a bullet shot against it. Now what will happen if you shoot many bullets across this cotton ball? Most of them will travel straight through the cotton surface. What will happen if a bullet hits the edge of the central heavy mass? In this case, the bullet will slightly change their path and get deviated. So looking at the size of the central mass, it's obvious that only some of the bullets will get deviated. Lastly, what happens when a bullet hits the center directly? Needless to say, it will bounce back, because we know that the central dense mass is too hard for the bullet to pass through. So very few bullets will bounce back. This is analogous to what Rutherford had inferred about the atomic structure. His first conclusion was that most of the space inside an atom is empty. This is because most of the alpha particles could easily pass through the atoms and hit the detector straight. Now, if most of the space is empty inside an atom, then where is the positive charge located? Well, that's the second conclusion. The positive charge is compactly packed in a tiny entity. This occupies an extremely small space inside the atom. Now, why did he think so? Let's go back to our cotton ball and bullet example. Can you recall the second and the third case? Yes, The bullets get deviated on hitting the tiny sphere of the edge, and they will rebound when they hit the center. Same explanation holds true for this. A few alpha particles get deviated. That means there is a possibility that these hit the edge of the positive center. Yes, and one more possibility is that they get deviated because the positive center repels the alpha particles as they're also positively charged. Also, a very small number of alpha particles rebounded. That means there is a possibility that these alpha particles had directly hit the positive center. But since the number of these rebounding particles is too small, it explains that the volume occupied by the positive center is also very small. If the space occupied would have been big enough, then the number of alpha particles bouncing back would also be greater. So let's say there are gold particles in the foil. He found that most of the rays pass straight through the atoms. A few rays change their path and get deflected. Lastly, very few particles bounce back. These results compelled Rutherford to come up with a new nuclear model. Let's have a look at the hypothesis put forward by him. Firstly, there's a positively charged center in an atom called nucleus. Nearly all the mass of an atom resides in the nucleus. Secondly, the electrons revolve around the nucleus in circular paths. Thirdly, the size of the nucleus is very small compared to the size of an atom. However, theoretically, there were many flaws in the hypothesis. Let's have a look at the drawbacks in Rutherford's hypothesis in the next video. Also, we will have a look at the explanation of atomic structure by another scientist named Niels Bohr in the next video. Rutherford's atomic model was quite commendable when it came to explaining the structure of atoms. However, it was not very appropriate theoretically. And why are we saying so? We know that any charged object which revolves in a circular motion gains acceleration gradually. Similarly, if the electron is moving fast in a circular path, then it will also gain acceleration. And on gaining acceleration, it's bound to liberate energy in some form. Now, if it continuously keeps radiating energy, then ultimately all the energy of the electron will get over and it will fall into the nucleus. This would result in high instability of the atom. But wait a second, all these things do not happen in an atom. And how do we know this? Because in nature, all the atoms are stable. That means the hypothesis put forth by Rutherford was also incorrect? Not really. The hypothesis just needed slight modifications. These were made by the next legendary scientist in our list called Niels Bohr. He made a few additional explanations to describe the atomic structure. The postulates put forward by Niels Bohr were as follows. Firstly, only certain special orbits called discrete orbits of electrons are allowed inside the atom. Secondly, while revolving in these discrete orbits, the electrons do not radiate energy. Now, these points definitely tell us why an atom is so stable. But what exactly are these paths or orbits in which the electrons revolve around the nucleus? Let's understand with an example. Do you know how our solar system is? Yes, it appears somewhat like this. Now here, the sun is stationary at the center while the planets revolve around it. But have you noticed that the planets always revolve in fixed paths? We never find any planet jumping to a different path all of a sudden, right? They always encircle the sun in defined paths. In a similar way, we have the atomic structure. The nucleus acts like the sun located at the center, and the electrons are like planets which revolve in fixed, defined orbitals. These electron orbitals are referred to as shells or energy levels. Now, the name energy levels gets us to an important concept. Niels Bohr suggested that the electrons revolving in these orbitals do not radiate energy. Now, this is justified when we use the term energy levels, because it indicates that each shell has got a defined energy level. That means when the electrons revolve in these shells, they do not liberate any form of energy. And how do we name these shells to indicate their position? It's simple. beginning from the one near the nucleus, we name them as the K shell, L shell, M shell, N shell, and so on. Yes, K, L, M, N, and so on. And what if we want to number them? In that case, we use the letter N in lowercase and write them as N equals 1, N equals 2, N equals 3, and so on, beginning from the one next to the nucleus. So we can name them alphabetically, or we can even number them. With all these theories and points known, do we now know the structure of a typical atom completely? The nucleus contains positive protons and the electrons revolving around in fixed orbitals. Is that how an atom is structured? Not really. We still have one more subatomic particle left. And what and where could it be? Let's find that out. It was around the year 1932 when a famous English physicist, Sir James Chadwick, found the third subatomic particle. He found that the particle had a mass almost equivalent to that of the proton. And what about its charge? Astonishingly, it had no charge. Yes, the particle was neutral. The particle was later named as neutron, denoted by the letter N. Thus, now we have the complete design of an atom. In the center lies the nucleus having positively charged protons and neutral neutrons, while the negatively charged electrons revolve in fixed orbitals around the nucleus. But how exactly are the electrons distributed in the respective orbitals? Is there a way to find out the maximum number of electrons that one orbital can contain? Or is it that the electrons are randomly scattered in the orbitals? Let's find out the answers to these questions in our upcoming video.